Imagine this. Okay, two massive black holes out there in the cosmos, spiraling towards each other. They finally merge.
A huge event.
But instead of just settling down, the new, bigger black hole gets, well, kicked violently across the universe. Today, we're doing a deep dive into something based on the material you shared with us, this idea of gravitational wave rockets.
That's right. And this dive, it really stems from the specifics in that material, looking at what happens when supermassive black holes merge. The central idea is that, well, these mergers aren't always perfectly neat and symmetrical.
Right, and the material digs into why that asymmetry is so crucial. If the black holes have, say, different masses, or maybe their spins are tilted, not lined up, then the gravitational waves they blast out during that final plunge, it's not an even burst in all directions. It's lopsided.
Exactly. Think of it like recoil. A really powerful recoil. That uneven burst of gravitational waves carries momentum mostly one way.
Ah, so to conserve momentum.
Precisely. The resulting single black hole gets a massive push, a kick, in the exact opposite direction.
And the speeds, according to this material, I mean, they can be incredible, up to a few percent of the speed of light.
It's astounding, isn't it? For an object that massive, it just shows the sheer power unleashed.
Wow.
So in this deep dive, and we're really sticking to the material you provided here, we'll unpack the mechanics of these gravitational wave rockets.
Okay.
We'll explore how we might actually, detect the events powering them. And then we get into the really speculative part.
The almost science fiction idea.
Yeah, the idea of maybe using this, or at least understanding its implications, for something like space travel.
So this is your shortcut, basically, to getting your head around this really complex but fascinating idea, all pulled straight from the insights in the material provided. Okay, let's dig in. How does the material describe this gravitational rocket effect?
Well, the material traces it back to some significant research. It notes that if the kick isn't too extreme, the black hole might actually slow down over time.
Slow down. How?
Through something called dynamical friction, basically drag from moving through all the stars and gas in the galaxy. It might even drift back towards the center it came from.
Interesting. And the scale here is just immense, right? We're talking supermassive black holes at the centers of galaxies.
Exactly. The material even mentions the future collision between our Milky Way and Andromeda.
Which is still billions of years away.
Billions, yes. But the eventual merger of their central black holes could potentially result in one of these huge kicks, too. It all depends on the specifics, of Sagittarius A and Andromeda's black hole.
So, okay, these things are happening potentially billions of light years away over these vast timescales. How on earth can we detect them? The material mentions the gravitational waves themselves.
Right. That's the primary signal. And this is where future missions like LISA come into play, the Laser Interferometer Space Antenna.
That's the European Space Agency mission planned for, 2035?
That's the one. It's specifically designed as a space-based observatory to catch gravitational waves from sources just like these merging supermassive black holes across cosmic history, really.
So LISA could hear the gravitational sound of the merger. But the material also talks about needing an electromagnetic counterpart. Why is that so important?
Well, finding a counterpart, seeing something in light, or X-rays or radio waves alongside the gravitational waves, that would be huge.
For pinpointing it.
Exactly. It would help us nail down its location on the sky much better, measure its redshift, figure out the distance, which then lets us use these events as standard sirens.
Standard sirens. Like standard candles, but with gravitational waves.
For cosmology.
Precisely. For mapping the universe's expansion. But, as the material points out, finding that light signal is tricky.
Yeah, it sounds really challenging based on the description.
It definitely is.
Yeah.
The material outlines a few possibilities, but they're all pretty subtle or maybe delayed. You might get a weak, quick flash from energy dissipation in the gas disk around the black holes as they merge. Okay, a quick flash. What else?
Maybe years later, you'd see a brightening in X-rays as the disk settles down, or even thousands of years later, perhaps some enhanced infrared light from shockwaves.
Shockwaves from what?
From the recoiling black hole smashing through interstellar gas as it flies out.
Wow. But separating those faint signals from all the other chaos near a galactic center, that sounds tough. You've got quasars flickering already.
That's a major challenge. And the material notes that the merging black holes themselves might actually clear out a lot of the nearby gas beforehand.
Like a blender, it says.
Yeah, essentially acting like a blender in the final stages, which could reduce how bright any immediate signal might be.
So less gas means less light.
Potentially. Although the material does mention that if some gas does manage to stay bound to the kicked black hole,
Uh-huh.
you might see it later as an offset quasar, a bright, active black hole, but, surprisingly far from the center of its host galaxy.
But that depends on enough gas surviving the whole merger and kick process.
Absolutely. It's a possibility, but not a guarantee.
Okay, so the material brings up another detection idea, one that doesn't rely on gas that was already there. Tidal disruption events.
Yes, TDEs. Because now you have this remnant black hole, basically a high-speed missile, shooting through the galaxy's star field.
It's bound to run into things.
Frequently. And when it gets close enough to a star, it can tidally rip it apart with its gravity.
And those events are bright.
They can be very bright, yes. Observable flares. The material suggests we could potentially see these even at huge distances, especially if the event launches a relativistic jet.
Okay, so TDEs are another potential signature. And the material also mentions that the speed of the kick itself isn't always the same.
Correct. It depends heavily on the properties of the merging black holes. Their mass ratio, how fast they're spinning, the orientation of those spins.
So some configurations produce bigger kicks than others.
Exactly. The biggest kicks, according to the material, seem to happen when you have rapidly spinning black holes whose spins are pointing in opposite directions relative to their orbit just before they merge. Highly asymmetrical.
Okay, so detecting involves listening for gravitational waves with things like LISA, hunting for these faint or delayed light signals, or maybe spotting stars getting shredded by the runaway black hole.
Yeah.
Now, let's shift gears to the part that sounds like pure sci-fi.
The space travel application.
Yeah, the material actually goes there. It contemplates using this effect.
It does, but framed very much as a speculative thought experiment, really highlighting the immense power scales involved.
How does it phrase it?
The material basically posits that the storm of gravitational waves near merging black holes is so intense it could transfer significant momentum to any object nearby. A planet, a star, or, yes, theoretically, a spacecraft.
Which leads to this, well, frankly, mind-bending scenario described. You'd need to somehow park a spacecraft incredibly close to a supermassive black hole.
Like maybe Sagittarius A at our galaxy center.
And then you just wait.
And wait. Possibly for billions of years.
Billions? For what?
For that black hole to merge with another one, like the eventual Milky Way-Andromeda merger, you'd have to be in the right place at the right multi-billion-year time.
To catch the wave, to get propelled by that gravitational kick.
That's the thought experiment presented in the material. It's less a practical proposal and more a way to, grasp the almost unimaginable power of these natural cosmic engines.
It's absolutely rooted in extreme physics, which the material explores well. But then the material pivots, doesn't it? It shifts from cosmic mechanics to, well, the mechanics of science itself.
Yes, it's a fascinating turn. The material brings up this discussion about whether finding truly groundbreaking discoveries is getting harder.
And the perspective offered is, yes, it is.
Yes. And it suggests that part of the reason, maybe a less discussed one, is the actual culture within academia, within the scientific community.
How so? The material seems quite direct about it.
It suggests that sometimes established experts whose careers, whose status are built on the current understanding might, perhaps unconsciously, resist truly radical out-of-the-box ideas.
Because it challenges the status quo they dominate.
That's the implication. And this resistance, the material argues, can show up in ways like blocking publications or maybe dismissing or even ridiculing unconventional approaches.
And the material points out the pressure this creates, especially for younger scientists.
Exactly. It suggests this kind of environment can discourage researchers who might otherwise take more intellectual risks from really pursuing those far-out ideas. It kind of encourages everyone to stick closer to the mainstream.
A sort of regress to the mean effect, as the material puts it.
Yes. And it argues that in today's very large, very interconnected scientific world, these social pressures get amplified. Even mentions social media as potentially adding pressure that suppresses dissenting views.
So the material draws a really interesting parallel. It connects the cosmic rockets, these physical engines of immense power, to what it sees as the real drivers of human progress.
Precisely. The conclusion drawn in the material is that if we really want to spark innovation, to push boundaries, we should actively encourage non-traditional thinking. We should foster work on those really big, fundamental questions.
Questions that resonate with deep human curiosity.
Yes, things like, are we alone? Or what are the ultimate limits of intelligence? The material suggests that pursuing those kinds of challenging, potentially disruptive questions while those are the actual rockets that will propel humanity forward. More so, perhaps, than focusing only on incremental progress within established frameworks.
That's a really provocative link, isn't it? From gravitational wave physics to the sociology of science.
It certainly raises important points about how we cultivate environments that truly support bold, maybe even uncomfortable new ideas in science.
Okay, let's do a quick recap then of this deep dive, based entirely on the material you shared about gravitational wave rockets. We explored how these asymmetric mergers of supermassive black holes can generate this incredibly powerful kick.
A kick driven by gravitational waves, capable of flinging the resulting black hole remnant at potentially a few percent of light speed. Just incredible velocities.
And we talked about how future missions, like LISA, are being designed specifically to detect the gravitational waves from these events.
And also the challenges and the potential methods the material described for finding those elusive electromagnetic counterparts, be it faint flashes, delayed X-rays, or even spotting stars getting torn apart, the TDEs.
Right, the tidal disruption events from the black hole speeding through its galaxy. And we definitely touched on the material's highly speculative but really fascinating thought experiment.
Yeah, about maybe, just maybe, harnessing this natural power for space travel, involving that almost unthinkable weight near a black hole for a merger event potentially billions of years in the future.
And finally, we explored how the material connected all this cosmic mechanics to a broader commentary.
A commentary on the challenges that truly disruptive scientific ideas can face, within the current academic and scientific culture. That idea of resistance to genuinely out-of-the-box thinking, potentially slowing progress.
And the material's proposal that actively pursuing those brave, unconventional, fundamental questions, those are the real engines for human advancement.
Exactly.
So, thinking about the sheer power we see in nature, like these black hole mergers, and reflecting on the material's perspective about the power of disruptive ideas, it leaves us with a thought, doesn't it? What unconventional ideas bubbling up in science today, ideas that might seem impossible now, maybe they're being pushed to the margins. What ideas do you think might actually hold the key for humanity's future understanding and exploration of the universe? It's a powerful connection to ponder, drawn straight from the insights presented in this material.